So we have very many carbohydrates. When we talk about carbohydrates, we have very many types of molecules that differ according to how many carbon atoms they actually have, or how many saccharide units they actually have. So you can have a simple linear carbohydrate, but you can also have a very complex carbohydrate. Okay, that is very long and also highly folded, for example, highly branched. Okay, so we can talk about monosaccharides, disaccharides, we can talk about polysaccharides. Okay, these are the three categories of carbohydrates that we are going to look at. Okay, so when you see the word mono, usually means something that is actually one. So monosaccharides are basically the simplest carbohydrates that you can have. Okay, you have single sugar molecules. So in this case, for example, you have a molecule of glucose, you have a molecule of fructose, and then a molecule of galactose. Okay, um, what do they really have? They have what you call the carbonyl group, uh, which can be either the aldose or the ketose. Um, and then the different number of carbon atoms that they actually have. This is what differentiates them. So we have the three that I have already indicated, glucose, fructose, galactose, and then also ribose there. We shall see that ribose actually is what you find in the RNA. Okay, so if we talk about the properties of monosaccharides, just think about glucose. If you think about glucose, you'll be able to get the properties. Glucose is sweet, right? Yes. If whether you have this it in powder form, whether you have it in crystalline form, it's sweet. Okay, it's soluble in water. That is to say that when you dissolve it in water, you will not see it will basically dissolve within it. Okay, this basically happens because of the OH group. The OH group is actually one of the functional group, like I said, in carbohydrates. Okay, so this actually forms what we call hydrogen bonds with water, and that's why it basically dissolves in water. Okay, so we basically say that this glucose is actually when you dissolve, basically you have that association in terms of forces of attraction forming hydrogen bonds. Okay, and then you can also have actually these are actually reducing sugars, and I already explained this using the Benedict test that I talked about. So, like I said, monosaccharides are not very complex. So you cannot find because they actually exist as molecules, like we saw, simple sugar molecules. That is what we said. So you don't have them combining to form, for example, long chains. So that's why we have them existing either as um, molecules, sugar molecules of either three carbon atoms or even up to seven. So depending on the number of carbon atoms, we can call them different names. For example, those that have three carbon atoms, we can call them thioses. Okay, those are sugar molecules with three carbon atoms. And then tetraioses are the ones that have four. Pentoses have five, and then hexoses that have six, and then heptoses are the ones that have 7. Okay, okay, depending on the number of carbon atoms that we are having. So glucose is the most abundant of the hexoses. This is basically to say that you have many uh, sugar molecules that can have 6 carbon atoms. Okay, there are very many. Okay, just like what we saw earlier on with the fructose and the others, galactose. You can have them having 6 carbon atoms. Okay, But this is not to say that, for example, one that has 6 carbon atoms is only one molecule. You can have very many sugar molecules that have 6 carbon atoms. But so we are saying glucose is the most abundant exose. This is to say it's the most abundant carbohydrate that has 6 carbon atoms, and its chemical formula is actually that 6 carbon atoms, 12 hydrogen atoms, and then 6 oxygen atoms. And therefore, it actually has this ring that you see here. Okay, that is glucose. It exhibits what we call isomerism. Isomerism is a concept that relates to the fact that you can have the same molecule, but that same molecule can have different structural forms or structural appearance. This is to say, like, you see that this carbon has 6 carbon atoms, 12 hydrogen atoms, and then 6 oxygen atoms. But the way this can actually be arranged can be different. There are several ways in which you can arrange all these atoms. So what we have been explaining is that glucose exhibits what we call isomerism. So with isomerism, you have a compound that has its molecular formula, but that same molecular formula can be arranged differently, such that you have different structural appearances of that same compound. So this what we are saying, that glucose has 6 carbon atoms, 12 hydrogen atoms, and then 6 oxygen atoms. But the way these are arranged can be different, okay? But still it remains that you have the same glucose. So these different arrangements, the different forms of the same glucose are the ones that we call the isomers of glucose. Okay, so the isomers of glucose, we have 2 of them here, alpha glucose, and then we have the beta glucose. And what is happening here is that for alpha glucose, you have the OH group being below carbon 1, and then the beta glucose, you have the OH group being above carbon 1. Okay, that is what we refer to there. So usually with these organic compounds, when we are naming them, when we are giving them their names, which we often call the nomenclature of organic compounds, we start with the shortest distance from the carbon atom that has the functional group. So we start naming from that carbon atom. Okay, so the carbon atom that has the functional group is carbon atom number 1. Okay, so what we are saying here is that with the alpha glucose, with that carbon atom number 1, you have the OH group above that carbon atom number 1, and then with the beta, you have the OH group, which is basically the hydroxyl group, being below carbon 1. And consequently, this is why we have different carbohydrate storage forms in animals and plants. In plants, we have the alpha glucose forming starch. This is to say that the alpha glucose forms starch in plants, and then the beta glucose forms cellulose, also still in plants. So other exoses, this is to say other carbohydrate molecules that have 6 carbon atoms. We have fructose and then galactose. Fructose, it is what we call the fruit sugar. So if you get a fruit, it could be a mango, that the sugar that you have there is what we call fructose. Okay, and then you have galactose, which is an important element in, for example, lactose, which is the sugar that we find in milk. And then pentoses, the ones that have 5 carbon atoms. We have ribose and then deoxyribose. So the ribose is what we find in RNA, and then deoxyribose is what we find in the DNA. So this is a simple illustration of what DNA is like. Okay, so DNA has a sugar, what we call a pentose sugar, a sugar that has 5 carbon atoms, and the nitrogen bases. Okay, and then the nitrogen bases, and then these ones here, these are the ones we call the nitrogen bases. Okay, and these nitrogen bases are actually pair. They pair with one another. They pair with one another, what we call nitrogen base pairing, or what we basically call base pairing. Okay, so you have the bases include adenine, guanine, thymine, and then cytosine. Okay, so these bases actually pair following a convention. This is to say that adenine pairs with thymine, for example. They don't just pair; they follow the pairing rules. So when we look at the structure of DNA, and then we talk about the base pairing, you should be able to know which base pairs with which one. So this is one strand of the DNA, and then this is another strand of the DNA. So that strand is made because of the pentose sugars. Okay, and then what extends outwards to form the base pairings are the nitrogen bases. So when looking at the nucleic acids, I think that is a good starting point for you. So simple sugars, the ones that we have just talked about, the glucose, the galactose, and the other sugars. What do we use them for? For example, the glucose is what usually the body relies on for energy. Okay, so it gives us energy. The energy can be in terms of kilojoules per gram. So when you have, if you have 1 gram of glucose, and then it is actually burnt, that is respiration, to give you energy. How much energy do we get? So we are saying here it is approximately 16 kilojoules per gram during respiration. And then you also need to know how much energy do we get from proteins, for example, from 1 gram of proteins, from 1 gram of, let us say, lipids. What do we get? Okay, that's something that you need to check out. Lactose is the sugar that we get in milk, and then maltose it's produced from amylose breakdown in germinating seeds. So when seeds are basically germinating, the stored carbohydrates have to be broken down, and one of those is maltose, and then it is used for uh, generating the energy after respiration. Okay, and then we have sucrose, which is the sugar that we actually the table sugar, that is actually sucrose. We get that sugar, or we get that form of carbohydrates